So today I'm going to present my paper, Evolutionary Optimization of Deep Learning Agents for Sparrow Mahjong. And first to introduce the game of Mahjong. Mahjong is an ancient game originated from China, played with 3 or 4 players. It's a tile-based game. And as you see in this picture, the players have their own tiles while they are not able to see the tiles of the other players. And at the same time, when the players pick the tiles from the middle in each round, they cannot know which tile they are picking. And they can discard tiles, and this is how you can have information of the other tiles in the game other than the ones in your hand. And this is why Mahjong is an imperfect information game. And Sparrow Mahjong, in short, is a simplified version of Mahjong where each player has 5 tiles, and each turn you grab a tile from the middle stack which you cannot see, or you grab a tile from the discarded pile of tiles that the player before you discarded. And then you will have 6 tiles, and you discard one in each round, and you can choose which tile to discard. And the game ends when the tiles in the middle finish, or someone else in the game is able to form a winning hand, which is generally creating a hand of pairs, a triplet, or a different winning combination of hands. And as you can see on the top middle, there is a gray box which shows the Dora tile. That gives you an extra score when you have in your hand. And this is basically Sparrow Mahjong, which is a simpler version of Mahjong, and we decided to use it because PGX environment provides a fast way to evaluate agents in Sparrow Mahjong. And as it's a simplified version of Mahjong, we do not have to deal with all the complexity of Mahjong while proposing an agent to play it. So our agent basically utilizes a long short-term memory network. And in this network, we input 3 different main things. The first thing is the Dora tile, which is the top gray tile I showed in the previous slide. And the discards of the 3 players throughout the game, because that's an information we can see, and the hand of our hand in the game, which is with the 6 tiles. And this is passed through 3 LSTM layers and 8 fully connected layers, which all have tiles of 32, and our network decides which tiles to discard. And in short, we optimize the weights of this long short-term memory network using CMAES. And we compared our agent against 3 main baseline agents. First of all, we compared our agent against a random agent, where the player basically chooses which tile to discard completely randomly. And then we developed a rule-based agent, which has around 13 rules, and it's able to use some basic heuristics of the game to decide which tile to discard. It can be described as a player who knows the rules of the game really well. It never breaks up a tile set it created, or it looks at the discards of the player after it, and it tries not to discard a tile that can help the next player. And lastly, we compared our agent against a PPO optimized agent, which we use the proximal policy optimization to optimize the agent. And these are the results. Our Evo Sparrow agent was able to outperform the rule-based agent and random agent, both in the win percentage and at the same time the loss percentage and the deal-in percentage. And at the same time, when we compared with the PPO Sparrow, which is a PPO optimized agent, it was on par with the PPO Sparrow agent. And by the way, this is a result of 1 million games. So while the percentages are really close, we ran it for 1 million times to be sure about our results. And lastly, we also evaluated our agent in self-play. And we also ran our training completely from scratch for 100 independent training runs, and we showed the medium fitness and 25 and 75 percentile fitnesses in this graph, just to be sure that our agent was not created by chance and it's a constant success. And the future work, we are planning to implement opponent modeling to improve predictive accuracy and adaptability. And we are planning to extend the architecture to support more complex neural models, like we can trade different neural architectures or different optimization methods. And as I explained earlier, we have a very simple state representation where we encode the tiles directly when we can explore more richer state representations for the game. And we are planning to apply this proposed methodology to other stochastic and hidden information games. We are planning to apply it to Mahjong and to games such as Mahjong. And thank you. And I can take questions as well if there's any.
Thank you. We have a quick question. Yes, go ahead. Okay, so the question is, what is the advantage of your model compared to existing commercial Mahjong AI?
As far as in our related work section, we talked about as well. Existing Mahjong AI required a lot of training data, and also it was not using an evolutionary computation method. And one of the things we emphasize in our paper is the PPU optimized agent. We say we train it with the exact same configurations, and because the CMAES by nature can be evaluated in parallel, it's able to train much faster. And we wanted to provide an evolutionary computation, the different baseline to the area rather than the popular, like the streamlined Mahjong agent.
Okay, thank you.
Sounds good. Thank you.
Thank you.